In radio, multiple input and multiple output, or MIMO, pronounced ʻmaɪmoʊ or ʻmiːmoʊ, is a method for multiplying the capacity of a radio link using multiple transmit and receive antennas to exploit multipath propagation. MIMO has become an essential element of wireless communication standards including IEEE 802.11n, Wi-Fi, IEEE 802.11 AC, Wi-Fi, HSPA+, 3G, WiMAX, 4G, and long-term evolution, 4G. More recently, MIMO has been applied to powerline communication for three-wire installations as a part of ITU G.hn standard and HomePlug AV2 specification. At one time, in wireless the term MIMO referred to the use of multiple antennas at the transmitter and the receiver. In modern usage, MIMO specifically refers to a practical technique for sending and receiving more than one data signal simultaneously over the same radio channel by exploiting multipath propagation. MIMO is fundamentally different from smart antenna techniques developed to enhance the performance of a single data signal, such as beamforming and diversity. History. Early research. MIMO is often traced back to 1970s research papers concerning multi-channel digital transmission systems and interference, crosstalk, between wire pairs in a cable bundle. R.K. and R. George. 1970. Brandenburg and Winner. 1974. And W. Van Etten. 1975. 1976. Although these are not examples of exploiting multipath propagation to send multiple information streams, some of the mathematical techniques for dealing with mutual interference proved useful to MIMO development. In the mid-1980s, Jack Saltz at Bell Laboratories took this research a step further, investigating multi-user systems operating over mutually cross-coupled linear networks with additive noise sources, such as time division multiplexing and dually polarized radio systems. Methods were developed to improve the performance of cellular radio networks and enable more aggressive frequency reuse in the early 1990s. Space division multiple access (SDMA) uses directional smart antennas to communicate on the same frequency with users in different locations within range of the same base station. An SDMA system was proposed by Richard Roy and Bjorn Ottersten, researchers at Arraycom. In 1991, their U.S. patent, No. 5515378 issued in 1996, describes a method for increasing capacity using an array of receiving antennas at the base station, with a plurality of remote users. Quote, Invention. Era G.hn. Paul Raj and Thomas Kailath proposed an SDMA-based inverse multiplexing technique in 1993. Their U.S. patent, No. 5345599 issued in 1994, described a method of broadcasting at high data rates by splitting a high-rate signal into several low-rate signals, to be transmitted from spatially separated transmitters, and recovered by the receive antenna array based on differences in directions of arrival. Paul Raj was awarded the prestigious Marconi Prize in 2014 for his pioneering contributions to developing the theory and applications of MIMO antennas. His idea for using multiple antennas at both the transmitting and receiving stations, which is at the heart of the current high-speed Wi-Fi and 4G mobile systems, has revolutionized high-speed wireless. Quote, in an April 1996 paper and subsequent patent, Greg Raleigh proposed that natural multipath propagation can be exploited to transmit multiple independent information streams using co-located antennas and multidimensional signal processing. The paper also identified practical solutions for modulation, µMIMO FDM, coding, synchronization, and channel estimation. Later that year, September 1996, Gerard J. Foschini submitted a paper that also suggested it is possible to multiply the capacity of a wireless link using what the author described as layered space-time architecture. Quote, Greg Raleigh, V. K. Jones, and Michael Pollock founded Clarity Wireless in 1996, and built and field-tested a prototype MIMO system. Cisco Systems acquired Clarity Wireless in 1998. Bell Labs built a laboratory prototype demonstrating its V-Blast vertical Bell Laboratories layered space-time technology in 1998. Araji Paul Raj founded IOSpan Wireless in late 1998 to develop µMIMO FDM products. IOSpan was acquired by Intel in 2003. V-Blast was never commercialized, and neither Clarity Wireless nor IOSpan Wireless shipped µMIMO FDM products before being acquired. Standards and commercialization. MIMO technology has been standardized for wireless LANs, 3G mobile phone networks, and 4G mobile phone networks and is now in widespread commercial use. Greg Raleigh and V. K. Jones founded Ergo Networks in 2001 to develop µMIMO FDM chipsets for wireless LANs. The Institute of Electrical and Electronics Engineers, IEEE, created a task group in late 2003 to develop a wireless LAN standard delivering at least 100 Mbit per second of user data throughput. There were two major competing proposals. TGN Sync was backed by companies including Intel and Philips, and WiMAX was supported by companies including Ergo Networks, Broadcom, and Texas Instruments. Both groups agreed that the 802.11n standard would be based on µMIMO FDM with 20 MHz and 40 MHz channel options. TGN Sync, WiMAX, and a third proposal, ʻmaɪmoʊ, backed by Motorola and Mitsubishi, were merged to create what was called the Joint Proposal. In 2004, Ergo became the first company to ship µMIMO FDM products. Qualcomm acquired Ergo Networks in late 2006. The final 802.11n standard supported speeds up to 600 Mbit per second, using 4 simultaneous data streams, and was published in late 2009. Surendra Babu Mandava and Araji Paul Raj founded Beam Communications in 2004 to produce µMIMO FDM chipsets for WiMAX. The company was acquired by Broadcom in 2010. WiMAX was developed as an alternative to cellular standards, is based on the 802.16e standard, and uses µMIMO FDM to deliver speeds up to 138 Mbit per second. The more advanced 802.16m standard enables download speeds up to 1 Gbit per second. A nationwide WiMAX network was built in the United States by Clearwire, a subsidiary of Sprint Nextel, covering 130 million points of presence. POP. By mid-2012, Sprint subsequently announced plans to deploy LTE, the cellular 4G standard, covering 31 cities by mid-2013 and to shut down its WiMAX network by the end of 2015. The first 4G cellular standard was proposed by NTT Docomo in 2004. Long-term evolution. LTE is based on µMIMO FDM and continues to be developed by the third-generation partnership project. 3GPP. LTE specifies downlink rates up to 300 Mbit per second, uplink rates up to 75 Mbit per second, and quality of service parameters such as low latency. LTE Advanced adds support for picocells, femtocells, and multi-carrier channels up to 100 MHz wide. LTE has been embraced by both GSM, UMTS and CDMA operators. The first LTE services were launched in Oslo and Stockholm by Telia in 2009. Deployment is most advanced in the United States, where all 4 Tier 1 operators have or are constructing nationwide LTE networks. There are currently more than 360 LTE networks in 123 countries operational, with approximately 373 million connections. Devices. Functions. MIMO can be subdivided into 3 main categories: precoding, spatial multiplexing, EDM, and diversity coding. Precoding is multi-stream beamforming, in the narrowest definition. In more general terms, it is considered to be all spatial processing that occurs at the transmitter. In single-stream beamforming, the same signal is emitted from each of the transmit antennas with appropriate phase and gain weighting such that the signal power is maximized at the receiver input. The benefits of beamforming are to increase the received signal gain, by making signals emitted from different antennas add up constructively, and to reduce the multipath fading effect. In line-of-sight propagation, beamforming results in a well-defined directional pattern. However, conventional beams are not a good analogy in cellular networks, which are mainly characterized by multipath propagation. When the receiver has multiple antennas, the transmit beamforming cannot simultaneously maximize the signal level at all of the receive antennas, and precoding with multiple streams is often beneficial. Note that precoding requires knowledge of channel state information, CSI, at the transmitter and the receiver. Spatial multiplexing requires MIMO antenna configuration. In spatial multiplexing, a high-rate signal is split into multiple lower-rate streams, and each stream is transmitted from a different transmit antenna in the same frequency channel. If these signals arrive at the receiver antenna array with sufficiently different spatial signatures and the receiver has accurate CSI, it can separate these streams into almost parallel channels. Spatial multiplexing is a very powerful technique for increasing channel capacity at higher signal-to-noise ratios, SNR. The maximum number of spatial streams is limited by the lesser of the number of antennas at the transmitter or receiver. Spatial multiplexing can be used without CSI at the transmitter, but can be combined with precoding if CSI is available. Spatial multiplexing can also be used for simultaneous transmission to multiple receivers, known as space division, multiple access, or multi-user MIMO, in which case CSI is required at the transmitter. The scheduling of receivers with different spatial signatures allows good separability. Diversity coding techniques are used when there is no channel knowledge at the transmitter. In diversity methods, a single stream, unlike multiple streams in spatial multiplexing, is transmitted, but the signal is coded using techniques called space-time coding. The signal is emitted from each of the transmit antennas with full or near-orthogonal coding. Diversity coding exploits the independent fading in the multiple antenna links to enhance signal diversity. Because there is no channel knowledge, there is no beamforming or array gain from diversity coding. Diversity coding can be combined with spatial multiplexing when some channel knowledge is available at the transmitter. Forms: multi-antenna types, multi-antenna MIMO, or single-user MIMO. Technology has been developed and implemented in some standards, e.g. 802.11n products. SISO, CMO, MISO are special cases of MIMO. Multiple input and single output. MISO is a special case when the receiver has a single antenna, single input and multiple output. CMO is a special case when the transmitter has a single antenna, Single input, single output. SISO is a conventional radio system where neither transmitter nor receiver has multiple antenna. Principal single-user MIMO techniques. Bell Laboratories Layered Space-Time. Blast. Gerard. J. Foschini. 1996. Per antenna rate control. Park. Varanasi. Guess. 1998. Chung. Huang. Lozano. 2001. Selective per antenna rate control. Spark. Ericsson. 2004. Some limitations. The physical antenna spacing is selected to be large. Multiple wavelengths at the base station. The antenna separation at the receiver is heavily space-constrained in handsets. Though advanced antenna design and algorithm techniques are under discussion. Refer to multi-user MIMO. Multi-user types. Recently, results of research on multi-user MIMO technology have been emerging. While full multi-user MIMO, or network MIMO, can have a higher potential. Practically, the research on partial multi-user MIMO, or multi-user and multi-antenna MIMO technology is more active. Multi-user MIMO, µ-MIMO, in recent 3GPP and WiMAX standards. µ-MIMO is being treated as one of the candidate technologies adoptable in the specification by a number of companies, including Samsung, Intel, Qualcomm, Ericsson, Huawei, Philips, Nokia, and Freescale. For these and other firms active in the mobile hardware market, µ-MIMO is more feasible for low-complexity cell phones with a small number of reception antennas, whereas single-user µ-MIMO's higher per-user throughput is better suited to more complex user devices with more antennas. Enhanced multi-user MIMO. 1. Employs advanced decoding techniques. 2. Employs advanced precoding techniques. SDMA represents either space division, multiple access, or super division, multiple access, where super emphasizes that orthogonal division such as frequency and time division is not used, but non-orthogonal approaches such as superposition coding are used. Cooperative MIMO. CO-MIMO uses multiple neighboring base stations to jointly transmit, receive data to, from users. As a result, neighboring base stations don't cause intercell interference as in the conventional MIMO systems. Macrodiversity MIMO, a form of space diversity scheme which uses multiple transmitter-receive base stations for communicating coherently with single and multiple users which are possibly distributed in the coverage area, in the same time and frequency resource. The transmitters are far apart in contrast to traditional microdiversity MIMO schemes such as single-user MIMO. In a multi-user macrodiversity MIMO scenario, users may also be far apart. Therefore, every constituent link in the virtual MIMO link has distinct average link SNR. This difference is mainly due to the different long-term channel impairments such as path loss and shadow fading which are experienced by different links. Macrodiversity MIMO schemes pose unprecedented theoretical and practical challenges. Among many theoretical challenges, perhaps the most fundamental challenge is to understand how the different average link SNRs affect the overall system capacity and individual user performance in fading environments. MIMO routing. Routing a cluster by a cluster in each hop, where the number of nodes in each cluster is larger or equal to 1. MIMO routing is different from conventional SISO routing since conventional routing protocols route node by node in each hop. Massive MIMO is a technology where the number of terminals is much less than the number of base station, mobile station, antennas. In a rich scattering environment, the full advantages of the massive MIMO system can be exploited using simple beamforming strategies such as maximum ratio transmission, MRT, or zero forcing. ZF. To achieve these benefits of massive MIMO, accurate CSI must be available perfectly. However, in practice, the channel between the transmitter and receiver is estimated from orthogonal pilot sequences, which are limited by the coherence time of the channel. Most importantly, in a multi-cell setup, the reuse of pilot sequences of several co-channel cells will create pilot contamination. When there is pilot contamination, the performance of massive MIMO degrades quite drastically. To alleviate the effect of pilot contamination, the workup proposes a simple pilot assignment and channel estimation method from limited training sequences. Applications. Spatial multiplexing techniques make the receivers very complex, and therefore they are typically combined with orthogonal frequency division multiplexing, OFDM, or with orthogonal frequency division multiple access, OFDM-A, modulation, where the problems created by a multipath channel are handled efficiently. The IEEE 802.16e standard incorporates MIMO OFDM-A. The IEEE 802.11n standard, released in October 2009, recommends MIMO OFDM. MIMO is also planned to be used in mobile radio telephone standards such as recent 3GPP and 3GPP2. In 3GPP, High-Speed Packet Access Plus, HSPA Plus, and Long-Term Evolution, LTE, standards take MIMO into account. Moreover, to fully support cellular environments, MIMO research consortia including IST Mascot propose to develop advanced MIMO techniques, e.g., multi-user MIMO, µ-MIMO. MIMO technology can be used in non-wireless communications systems. One example is the home networking standard ITU G.hn, which defines a powerline communications system that uses MIMO techniques to transmit multiple signals over multiple AC wires. Phase, neutral and ground. Mathematical description. In MIMO systems, a transmitter sends multiple streams by multiple transmit antennas. The transmit streams go through a matrix channel which consists of all N, T, N, R. Display style, script style N underscore T, N underscore R. Paths between the N, T. Display style, script style N underscore T. Transmit antennas at the transmitter and N, R. Display style, script style N underscore R. Receive antennas at the receiver. Then, the receiver gets the received signal vectors by the multiple receive antennas and decodes the received signal vectors into the original information. A narrowband flat-fading MIMO system is modeled as Y equals H X plus N. Display style mathbf Y equals mathbf H mathbf X plus mathbf N, where Y display style script style mathbf Y and X display style script style mathbf X are the receive and transmit vectors, respectively, and H display style script style mathbf H and N display style script style mathbf N at the channel matrix and the noise vector, respectively, referring to information theory. The ergodic channel capacity of MIMO systems where both the transmitter and the receiver have perfect instantaneous channel state information is C P E R F E C T minus C S I equals E max Q T R Q 1 log 2 det I plus rho H Q H equals E log 2 det I plus rho D S D display style C underscore mathroom perfect CSI equals E left max underscore mathbf q backslash mbox tr mathbf q leq1 log underscore 2 det left mathbf I plus row mathbf h mathbf q mathbf h caret h right equals E left log underscore 2 det left mathbf I plus row mathbf d mathbf s mathbf d right closing curly bracket where h display style script style caret h denotes Hermitian transpose and row display style script style row is the ratio between transmit power and noise power, i.e. transmit SNR. The optimal signal covariance Q equals V S V H. Display style script style mathbf Q equals mathbf VSV caret H is achieved through singular value decomposition of the channel matrix U D V H equals H. Display style script style mathbf UDV caret H equals mathbf H and an optimal diagonal power allocation matrix S equals diag S 1 S min n T n R 0 0. Display style script style mathbf S equals text rm diag S underscore 1 L dots S underscore min n underscore T n underscore R closing curly bracket 0 L dots 0 closing curly bracket. The optimal power allocation is achieved through water filling, that is, S I equals mu minus 1 rho d I 2 plus 4 I equals 1 min n T n R. Display style S underscore I equals left mu frac 1 rho d underscore I caret 2 right caret plus quad text rm 4 backslash I equals 1 L dots min n underscore T n underscore R closing curly bracket where d 1 d min n T n R. Display style script style d underscore 1 L dots d underscore min n underscore T n underscore R closing curly bracket are the diagonal elements of D. Display style script style mathbf D plus display style script style C dot caret plus is 0 if its argument is negative, and mu display style mu is selected such that S 1 plus plus S min n T n R equals n T. Display style script style S underscore 1 plus L dots plus S underscore min n underscore T n underscore R equals n underscore T. If the transmitter has only statistical channel state information, then the ergodic channel capacity will decrease as the signal covariance Q display style script style mathbf Q can only be optimized in terms of the average mutual information as C S T A T I S T I C A L minus C S I equals max Q E log 2 det I plus rho H Q H display style C underscore mathroom statistical CSI equals max underscore math BF Q E left log underscore 2 det left math BF I plus row math BF H math BF Q math BF H caret H right closing curly bracket. The spatial correlation of the channel has a strong impact on the ergodic channel capacity with statistical information. If the transmitter has no channel state information, it can select the signal covariance Q display style script style math BF Q to maximize channel capacity under worst case statistics, which means Q equals 1/n/T/I display style script style math BF Q equals 1/n_T math BF A, and accordingly C N O minus C S I equals E log 2 det I plus rho n T H display style C underscore mathroom no CSI equals E left log underscore 2 det left math BF I plus frac rho n underscore T math BF H caret H right closing curly bracket. Depending on the statistical properties of the channel, the ergodic capacity is no greater than min n T n r display style script style min n underscore T n underscore r closing curly bracket times larger than that of a SISO system. Testing. MIMO signal testing focuses first on the transmitter-receiver system. The random phases of the subcarrier signals can produce instantaneous power levels that cause the amplifier to compress, momentarily causing distortion and ultimately symbol errors. Signals with a high PAR, peak-to-average ratio, can cause amplifiers to compress unpredictably during transmission. OFDM signals are very dynamic and compression problems can be hard to detect because of their noise-like nature. Knowing the quality of the signal channel is also critical. A channel emulator can simulate how a device performs at the cell edge, can add noise or can simulate what the channel looks like at speed. To fully qualify the performance of a receiver, a calibrated transmitter, such as a vector signal generator, VSG, and channel emulator can be used to test the receiver under a variety of different conditions. Conversely, the transmitter's performance under a number of different conditions can be verified using a channel emulator and a calibrated receiver, such as a vector signal analyzer, VSA. Understanding the channel allows for manipulation of the phase and amplitude of each transmitter in order to form a beam. To correctly form a beam, the transmitter needs to understand the characteristics of the channel. This process is called channel sounding or channel estimation. A known signal is sent to the mobile device that enables it to build a picture of the channel environment. The mobile device sends back the channel characteristics to the transmitter. The transmitter can then apply the correct phase and amplitude adjustments to form a beam directed at the mobile device. This is called a closed-loop MIMO system. For beamforming, it is required to adjust the phases and amplitude of each transmitter in a beamformer optimized for spatial diversity or spatial multiplexing. Each antenna element simultaneously transmits a weighted combination of two data symbols. Literature. Principal researches. Papers by Gerard J. Foschini and Michael J. Garnes. Foschini and Emre Telatar have shown that the channel capacity, a theoretical upper bound on system throughput, for a MIMO system is increased as the number of antennas is increased, proportional to the smaller of the number of transmit antennas and the number of receive antennas. This is known as the multiplexing gain, and this basic finding in information theory is what led to a spurt of research in this area. Despite the simple propagation models used in the aforementioned seminal works, the multiplexing gain is a fundamental property that can be proved under almost any physical channel propagation model and with practical hardware that is prone to transceiver impairments. Papers by Dr. Fernando Roses and Dr. Christian Oberle have shown that the entire MIMO SVD link can be approximated by the average of the SIR of µ channels. This leads to characterize the eigenchannels of n times n MIMO channels with n larger than 14, showing that the smallest eigenchannel distributes as a Rayleigh channel. The next four eigenchannels closely distributes as µ channels with m equals 4, 9, 25 and 36. And the n5 remaining eigenchannels have statistics similar to an additive white Gaussian noise ITU G.hn channel within 1 dB signal-to-noise ratio. It is also shown that 75% of the total mean power gain of the MIMO SVD channel goes to the top third of all the eigenchannels. A textbook by A. Paul Raj, R. Nabar and D. Gore has published an introduction to this area. There are many other principal textbooks available as well. Mobile Experts has published a research report which predicts the use of MIMO technology in 500 million PCs, tablets, and smartphones by 2016. Diversity multiplexing trade-off, DMT. There exists a fundamental trade-off between transmit diversity and spatial multiplexing gains in a MIMO system. Zheng and C. 2003. In particular, achieving high spatial multiplexing gains is of profound importance in modern wireless systems. Other applications. Given the nature of MIMO, it is not limited to wireless communication. It can be used for wireline communication as well. For example, a new type of DSL technology, gigabit DSL, has been proposed based on binder MIMO channels. Sampling theory in MIMO systems. An important question which attracts the attention of engineers and mathematicians is how to use the multi-output signals at the receiver to recover the multi-input signals at the transmitter. In Shang, Sun and Zhou, 2007, sufficient and necessary conditions are established to guarantee the complete recovery of the multi-input signals. See also GEDOMIS. Generic hardware demonstrator for MIMO systems. NIST UWB MIMO channel propagation measurements in the 2 to 8 GHz spectrum. Links to suggested readings in MIMO, WCSP Group. University of South Florida, USF. Introduction to Wireless MIMO, Theory and Applications. Introduction to Orthogonal Frequency Division Multiplexing. Covers OFDM and MIMO radio configurations. Computer World Quick Study MIMO. Meeting the test challenges of 4G LTE. The basics of OFDM. MIMO. The future of wireless. Test challenges for WiMAX, HSPA+, and LTE. The challenges of moving to MIMO systems. RF test system tackles 4x4 MIMO signals. The role of EVM measurements in characterizing amplifier modulation performance. Industry views. 4G systems bring new design and testing challenges. Instruments test MIMO data transmissions. Literature review of MIMO. Overview of MIMO and MIMO RFIC test architectures.